I feel like you should start.
Okay, I'll start.
Okay.
Let me introduce Peter Ozsvath.
Lecture 2. Okay. Well, thank you all for coming back. All right. So I finished about 70% of the talk I wanted to last time, which meant that I didn't actually, that there's like a remaining 30% that I could give. So I think maybe I'll do that. So raise your hand if you weren't here last time. Okay, so I'm sorry, maybe the first 10 minutes might not be, might miss a little bit of the background, but maybe not, maybe it'll be okay. So it might seem a little bit. So the what I wanted to, what I was talking about was some notes. Okay, so what we defined last time was a chain complex associated to a knot projection. But it wasn't quite a knot projection, it was one of these so-called grid diagrams for knots. So I'm going to call quickly. We took an n by n grid of squares. Every row has a single, and squares can be decorated by O's and X's, with the rule that every row has a single X in it, and every row has a single O in it, and similarly every column has a single X in it and a single O in it. So if you like, these are just two permutations on n letters, graphs of two permutations on n letters. We don't want O's and X's to land in the same square, so there's a little constraint on the permutation. And this represents a knot, and the way it represents a knot is that I connect the O marking with the X knot marking by a vertical segment, and then I do the same thing on horizontal segments, but my rule now is that my horizontals are always behind my verticals. And this is a graphical way of representing knots. Now, associated to this, we now define a chain complex. And the chain complex is generated by what we call Heegaard states. The Heegaard state, grid states, sorry, it's generated by grid states. There's a toroidal symmetry in this picture, so I can think of this as simply living on the torus. Any two pictures that differ on the torus are going to represent the same knot because I can move backwards that way, and I can move forwards that way. There's no obstruction. So this picture is really a toroidally symmetric picture. So we're going to think of it as living on the torus. And our generators of our chain complex, there are n factorial generators of our chain complex. They will correspond to elements of the symmetric group on n letters as well, except they're sort of offset by a half from the O and X markings. So we think of this as our torus as having n horizontal circles on it and n vertical circles on it. And so now we have n tuples of intersection points between the horizontal and vertical circles, again distributed so that every vertical circle has exactly 1 point on it, and every horizontal one has exactly 1 point on it. So this point is of course the same as this point is the same as that point. This is an example of a Heegaard state. Not an example of a grid state. Okay, so there are n factorial many of these creatures, and now we define a chain complex, which I'm going to write GC minus of a grid diagram, which is, now we're going to enhance our algebra a little bit. We're going to look at the polynomial algebra over the field of character, over Z mod 2. And join U1 up to UN. And we're going to take a a free module over that ring generated by these grid states, n factorial generators of these. And I now have to define a differential. So the differential is going to go from one grid state to another, apparently. We say that two grid states, yes?
Sorry, can you clarify what the U1 to UN are?
Sue, they're right now just formal variables.
Okay.
Okay, so they're the coefficients of my chain complex. Okay, so now I have to say what the differentials are.
I have also a question.
Yes.
Is there a relation between these red dots and the way you have? What is the relation between the red dots and the crosses and the zeros?
Nothing.
Oh, okay.
So there are n factorial many different choices of the red dots. Okay, and so now I'm going to talk about rectangles that connect two of these grid states. So these grid states, which correspond to elements of the symmetric group on n letters, I'm going to draw blue dots. So here's another one. This is one generator, here's a different one. It's a different one that differs from the first one in exactly two coordinates. So when you've got two different grid states that differ in exactly two coordinates, then you can find exactly 4 rectangles in the torus, which connect those two generators. So I'm going to call, let's call the red one P and the blue one Q. Here's a generator P and here's a generator Q. Then there are exactly 4, if there are any rectangles that, so what's a rectangle that connects two generators? It's a rectangle whose 4 corners are the 2 places where P and Q are different. And all other components of P and Q are meant to be the same. So typically, if you give me any 2 permutations, there's going to be no rectangle between them because they're going to differ more than 2 spots. But if they differ in exactly 2 spots, then I claim there are 4 rectangles in the torus which have, as their corners, the 4 spots where P and Q are different. There's this one, this one, this one, and that one. Okay? We're on the torus. 4 rectangles. Okay, now there's an orientation convention. The rectangles are all oriented by the orientation on the torus. Then I can horizontally go from P to Q, or I could horizontally, and then I'll go vertically from Q to P, or I can go horizontally from Q to P and vertically in the other direction. So I'm going to think of the ones which horizontally go from P to Q as the rectangles that go from P to Q. And the other 2 as rectangles that go in the other direction. So this is R1, this is oriented under R1, this is R2, this is R3, and this is R4. Okay? And now we're going to define a differential. The differential of a P is going to be a sum of all rectangles from P to Q of, but not all rectangles, only certain rectangles, of something times Q. Which rectangles do we not exclude? We don't want to include rectangles that contain X markings inside them. So we want X intersect R. Okay? What else do we not want on the interior of our rectangles? We don't want, so this rectangle is not allowed because it's got an X in it. Consider this rectangle. It has an X in it, so that makes it not allowed, but it's even more not allowed because it contains in its interior a PQ dot. So we don't want, so these are disallowed. We also disallow PQ dots in the interior. Right, so P and Q are differ at exactly the corners. So there are some places where they coincide. We don't want any of those places where they coincide to be in the interior of the rectangle. So we want the interior of R intersect P, which is equivalent to saying Q. This should be empty. And then, so this is where we use the X markings. And we use the O markings in our coefficient. So we're going to have a coefficient now. For each rectangle, I'm going to associate a monomial in the U's. And that monomial will just count which O markings are in the interior. So if like O3 and O7 are inside, then we want to say that that rectangle contributes a monomial U3 times U6. The second U1 to the number of times O1 intersects R, UN times the number of times ON intersects R, with the understanding these exponents are all zeros and ones. Okay, that's the chain complex. Clear enough? Okay, so
you have a notion of degree?
yes, we have two notions of degree. So I want a bigraded chain complex. Very good. So I'm going to have two-dimension formulas. The first observation is that, well, okay. Maybe that should have been the first observation. But before we have, what I claim is that's still me and that's still my title.
Sorry, can you say again what the O's are?
The O's are these O markings in the
Oh, okay.
picture, and we're going to label them.
Okay.
Okay? Great. Okay. So if this X marking weren't here, but it were somewhere else, then this would contribute O4, U4. Okay? Now, what I claim is, here's a little proposition. There exists a unique function n from grid states to the integers, which satisfies the following normalization. If I take the northwest marking to each O, that's a particular grid state. I look at all the O markings and I take its northwest corner. That's a particular grid state. I want that to be, so let's call that the northwest O. Wow. This grid state should have Maslov grading. Should have Maslov grading 0. This function is 0. And the second property that this function has is the following. This is why I have my notes. That if there's a rectangle from P to Q, then the Maslov grading of P minus the Maslov grading of Q should be equal to 1 minus twice the number of times R is contained in O. So these are two properties that uniquely characterize a function. Now, it should be pretty clear that these properties determine a function because the symmetric group is generated by all transpositions, and in fact, it's even generated by all transpositions that of consecutive elements, which is to say that given any two grid states, I can connect them by a sequence of rectangles that are very thick. And now, if I go from here to here, well, you know, that's, as I have a sequence of rectangles, that formula will tell you. Sorry, I want the rectangle to have no PP points in its interior. For this formula to be true, but that I can do if these rectangles are very thin, then they satisfy that property. And you can see that if I've got a rectangle from P to Q, I also have a rectangle back from Q to P. So if this one ups the Maslov grading by 1, the other one better take it back down by 1 for the Maslov grading to be well defined. But we're guaranteed an O marking in one of those two rectangles, and that's going to bring the Maslov grading down by 2 to make it well defined. So you expect these two formulas to be true. What's not maybe totally obvious is that this doesn't overdetermine the function. So you have to, you're going to write down a formula that works to give you this function. Okay, so that's a function. Yes.
Can I ask again about the first point? What does that mean?
There's a particular grid state
Yes.
which I can just immediately see. You give me any old grid diagram, it's got O markings somewhere.
Yes.
Well, I take the grid state that's exactly to the closest here. It's a particular grid state, and I want that particular grid state to have 0. You see,
For all the O's.
for all
we
those,
just put-
just put it right there. There's a that's a grid state. Okay, great. So
I feel like you already knew there was such a function before you put
yeah,
this
I
comment
already
on
knew
it.
there was a function.
Is there a way to read it off from some like winding number or something? I mean,
This is not the winding number. There's another function which is a winding number. Let me.
I mean, I think I know why you call it the Maslov number. But
Yeah.
All right. There's no
Yeah.
reasonable way to say this.
Okay. Yeah. So this is like a it's kind of the back of the book kind of answer that I'm giving in this extended first lecture. So
The verification that of the existence is just sit down and calculate, or is there a conceptual reason?
is there a conceptual reason why? Yeah, I mean, it exists because this is a special case of another theory where you can destabilize the picture. You don't have n factorial generators anymore. But if you ignore the x markings entirely, then you end up having a theory that you can destabilize, and you eventually have one generator, and that one generator should have grading 0. That's somehow the deeper reason. Yeah, it's okay. What I should now tell you is why. So now it should be clear that that grading over there drops by 1 under this boundary operator. Why? Because if Q appears in the boundary of P, then there is a rectangle from P to Q that has no PQs in its interior. It's got some number of U's in its inside. And I want it to drop grading by 1, except I want U to have grading 2. So what we want is that the UIs should have change grading by 2. So that now that's now then clear that the boundary drops grading by 1. Okay, so now let me define another grading, which is like a winding number, which is called the Alexander grading. Which is defined by, it's just simply defined by Alexander grading of P is equal to Maslov grading with respect to the O markings minus the Maslov grading with respect to the X markings. So this is the analogous thing using the X's instead of the O's. You take their difference, and I can't remember now if this is off by some constant or not. But what's clear from this definition is that Alexander grading of P minus the Alexander grading of Q is equal to the number of times X appears in your rectangle minus the number of times O appears in your rectangle for any rectangle that connects P to Q. And this now does have a very nice interpretation. If you orient your knot in some particular way, and you think of this picture as being planar, then the Alexander grading really is the winding number of the knot around each of the components of your pole. So that's the relationship between the Alexander grading and the winding number. the other thing that's clear from this definition is that if you say that U drops the A grading by 1, then the differential will now preserve the A grading. So the differential drops the M grading by 1 and it preserves the A grading. We now have a bigraded homology theory, and we can take its homology. Homology of this grid complex has a grading which is induced by this Maslov grading. It has another grading that's induced by the Alexander grading. And this is something that we could call GH minus. Okay? So, is that clear enough? So, bigraded theory, U acts on the gradings in some funny way. And it's a module over a polynomial algebra in invariants. And now there are a bunch of kind of fun elementary exercises. One is that multiplication by ui is always homologous to multiplication by uj. In fact, so multiplication by ui is chain homotopy to multiplication by uj. And the chain homotopy operator can be defined as follows. Suppose that ui belongs to this oi, and uj belongs to this oj, and there's an x that lives right exactly here. So the column that contains oj and the row that contains oi is blocked off by an x marking. Then you can define a homotopy operator which counts rectangles which cross exactly that x marking and no other x marking. And that's now an operator that goes from grid complex that raises dimension by 1. Oh, I'm sorry. Maybe before I do this, there's the argument, there's a statement that d squared equals 0. So d squared equals 0, that's now a completely combinatorial argument which has to do with how two rectangles can interact. So let me draw sort of one case. I've got two rectangles in the torus, and I've got a rectangle from P to Q, and then I've got another rectangle, let's say, from Q to T. And this one has some O markings in it, and that one has some other O markings in it. Well, if I first do this rectangle, and then do that rectangle, that's a path that goes from P to Q to T. But I could alternatively first do, you see, when I P and Q, I go from P to Q, well then this has to be also a component of P. So I could have done this rectangle first instead. I can chop up this region alternatively as this composite of two rectangles. And when I do this one first, then I get a different creature T, and I go down here, and well, this double composite contributes some monomial in U's. Well, this double composite will contribute the same monomial in U's because it's got the same geometric region. Okay, fair enough? And if one of them is blocked by an X marking, and so one of them is disallowed, then it turns out the other one's also going to be disallowed. So there's one other thing that can happen. The two rectangles can be disjoint, but the same argument works. So d squared equals 0. It's elementary to check. Now the next fancier remark that I wanted to say was that multiplication by ui is chain homotopic to multiplication by uj, and that's the homotopy operator counts rectangles that cross exactly that x marking. And then you have to check that boundary h plus h boundary is equal to, what is boundary h plus h boundary? Well, here's h. Boundary is going to be some other rectangle. I can chop that region up alternatively. So you see that almost all terms in boundary h plus h boundary cancel each other. There's one special sick thing that can happen, which is this thin rectangle followed by that thin rectangle. You see, the point is that when I said two rectangles can interact in various ways, there's one bad way that two rectangles can interact, which is that I can do one rectangle and then I can go, all the way around the torus, go back to where I started. Now usually that's blocked because every column has an x in it, so it didn't count. But here we're allowing this particular x. So now we're actually allowing a thin annulus that goes up like that. But that contains exactly once OJ. And then it goes back to where you started. So this is UJ. And the other thing that's allowed is this thin annulus that goes around that direction, and that gives you my UI. So this is why multiplication by UI is chain homotopic multiplication by UJ. So we see that our chain complex, which looked like the ring that it was defined over, depended on the size of the grid diagram. Well, all the U's are homotopic to each other, so we can just think of it as defined over Z2. Okay? And now there are yes.
Sorry. So there's like another factor, which is at the boundary h plus h boundary 0. Is that true?
Yeah. So what I was trying to argue was that boundary h plus h boundary has a bunch of terms in it, but most of them vanish. Most of them are terms where you're looking at a term in h, which is counting some big old fat rectangle, and then when you take boundary of that, then that's going to be some other rectangle. And usually, a configuration like that has an alternative decomposition, just like in the proof of d squared equals 0. The only case where you don't have an alternative decomposition is the case where they fit together to make an annulus.
Okay. But then why does this say that UJ and UI are homologous?
This is the H now is the chain homotopy between these two chain maps.
Okay.
It's like if I have two chain maps F and G, we say they're chain homotopic if there's an operator H which satisfies boundary H plus H boundary equals 0. When you have that, that means that these two chain maps induce the same map on homology. That's like one of these amusing homological algebra exercises, and this turns into a bunch of kind of amusing homological algebra calisthenics that one does here. By the way, this is this is completely elementary, and undergraduate can learn it. We were very excited about it when it first came out. We were doing these REUs during the summertime, and overheard a conversation between two students once saying, "Oh yeah, I'm learning singular homology theory. Yeah, it's just like grid homology, except you have space." Anyways, so yes, so this is sort of basic homological algebra that tells you that multiplication by U is homotopic to multiplication by UJ, so they act the same way. So you can think of it as a chain complex over a polynomial algebra in a single variable. Now, for those of you who were in my first lecture, we had a finite dimensional vector space, not a U module, but f of U module. But to get the finite dimensional vector space, you set U equals 0, which is to say, on the chain level, on the level of chains here, you pick your favorite U variable that you like, and you set that to be 0. Which is to say that in the differential, if like UI appears in your rectangle, then you just kill the whole term. Now, you might say, why do you kill just one term? Why don't you kill them all? And this is another kind of little favorite exercise in homological algebra. If you have n different variables that act homologously, and you only need to set one of them to 0. If you set the others to 0, you're going to start doubling the size of your homology unnecessarily. So sometimes the way I give this lecture is that I define another version where you set all the u's equal to 0. You kill this term, and you also ask for O's intersect R. So that now there's less algebra, but it turns out that the silly homology groups of this chain complex depend on the grid diagram. But what doesn't is when you take the dimension of the homology groups and you divide it by 2 to the n. So that's that sort of silly thing to try to do, as an algebraist, but this now is independent of n, of your grid diagram. Okay, what's the bottom line here? The bottom line is that we now have a creature, a chain complex associated with a grid diagram whose homology group I'm claiming as a not invariant. Now, and why? Well, so, yes?
Is there an invariant before you take u to 0, or only after you take u to 0?
You don't have to you can either take u to 0, then you get one invariant, or you can leave u.
And then still.
And then it's a different invariant. So it's a different invariant that's got more information in. So this was first discovered by Manoescu, myself, and Suchari Sharkar, and we identified it with the previously existing holomorphically defined invariant, and that's why it was an invariant. But there's actually a completely self-contained proof of its topological invariance, about which I'll just say a few minutes. So there's a theorem of Cromwell that says that if you have any thing that's associated to an invariant of grid diagrams, which is further invariant under the following three moves, one is called commutation moves. I'm going to draw them vertical for no good reason. If I've got an O and an X marking and another O and an X marking in the neighboring column, and they don't link each other. So what I don't want is OX, OX. This is not allowed. If they don't link each other, then you can just swap them. That's called the commutation move. And I just need that move, and I don't need three. I need two. I need that move, and I need another move, which is destabilization. Destabilization is the following democratic process. Assume that you have two rows and columns, and there's a little assume you have a little 2 by 2 square in your diagram, and assume that of those 4 squares, only one of them is not marked. So maybe this is X, X. Then, of course, this must have an O here somewhere, and this must have an O here somewhere. But what we want to do is we want to break down our bridges. We want to eliminate this, this horizontal circle, and we want to also eliminate this vertical circle. And then, almost all of these turn into these. I mean, this is empty over here, so it turns into a nice O-marked square. This turns into an O-marked square. And right here, they take a vote. And whichever marking is in the majority, that's what wins. So in this case, it's an X, so this becomes an X. So, this is called destabilization. So if you want to think of these, you can think of grid diagrams sort of as stick figures of your knot. And then stabilization just means I put a tiny little dent. That's where I go from here to here. And destabilization is when I just get rid of a little tiny dent. Okay, so these are, and there's a beautiful theorem of Cromwell that says that two grid diagrams represent the same knot if and only if they can be connected by a sequence of stabilizations and destabilizations. In fact, there are really beautiful ideas that go in here. This has been studied. There's a beautiful paper by Dinikov which shows that you can identify the unknot by the following procedure. Take any grid diagram consider a grid diagram and start trying to simplify it by doing commutations at will and only destabilizations, never stabilizations. Then his theorem is that the grid diagram represents the knot if and only if you can simplify to the 2 by 2 case. You don't ever have to stabilize if you're trying to find that unknot. By the way, I wrote this vertically. There's also the horizontal analog. Okay, any questions? So there's a completely self-contained proof of topological invariance that was discovered by Manuescu, myself, Ozsvath, and Thurston, using this. You just have to construct chain maps, chain homotopy equivalences between the chain complexes before and after commutation loop and before and after a stabilization loop. And you just write it down explicitly. I want to say one more thing about grid diagrams, and then I'll have finished my first lecture. Are there any questions? There's a there's the question that you can ask: what happens if you actually try to commute two columns that are linked? And the observation is that that corresponds to a crossing change. You can so what one can prove is that the grid homology of a knot k plus and a grid homology of a knot k minus. There's a chain map from here to here and a chain map back, such that when you double compose, then that's chain homotopic to multiplication by u. And what that tells you is that if you were to invert u, then this wouldn't be a very interesting knot invariant, because you inverse u. Then this would be a quasi-isomorphism. So one can prove that the grid homology somehow it's going to be an f of u module. I'm doing the minus theory right now. The grid homology group is going to be a cyclic modulo over f of u, and so it's going to have the form finite many copies of f of u modulo u to the d, some u torsion part, and some other u non-torsion part that doesn't depend anymore on the actual knot. It turns out that it's just one-dimensional. It's a copy of f of u. And what you can do is you can take this generator, so that is to say, very concretely, you've got these generators of the grid homology complex, and you have a U map. Then, if you take a typical generator and raise it and hit it with U to the D for D sufficiently large, you expect that to vanish. But in fact, what you expect is it's going to end up in a sort of one-dimensional vector space. So now what you can do is you can look at this f of u, and you can see where its top generator is concentrated. And it turns out, I mean, its generator is it has some bigrading. And what I can do is I can look at the Alexander grading of that generator. Take the Alexander grading of, so I can write it this way. Take the maximum degree, maximum of all s of those elements, h of k, that maximum s of any c in h of k minus, we call it gh minus k s, such that u to the d times s, u to the d times c is never equal to 0 for all of them. And I will play by minus 1. This is now an integral invariant that I can extract from the U module structure. So let me just draw this very concretely. Concretely, we have this blob of points and a tail of U's coming out of it. And what I do is the U operation, so this is my S D space. And there's a U operator which drops D by 2 and moves S down by 1. And what I'm saying is that there's exactly kind of one infinite tail of elements that are connected by U's. And typically, I'm out here, then U is going to kill it. So what I do is I find the maximum S value of anybody who lives forever. And that is a knot invariant called tau. A little exercise in the way the gradings work in that map, which I didn't show, shows that tau of k plus minus tau of k minus in absolute value is always less than or equal to 1. And that tells you that the absolute value of tau of k is a lower bound of the unknotting number of k. And so this is the invariant that can be used to give a combinatorial proof of the Milnor conjecture. So what I'm doing now is a reformulation of a beautiful proof by Sharkar. So we again, there's a holomorphic geometry proof that gives us lower bound, but here I'm giving a completely kind of elementary and combinatorial proof. Okay, so this was a plug for this perspective, and which was also described in a book on my homepage. I was, for those of you who missed the beginning of last talk, if you look at my homepage, there's a completely certified kosher free copy of a book by called Grid Homology for Knots and Rings. By me, and so you don't have to feel guilty. This is pre-negotiated. It's a completely legal free copy that you can read. That's chapter 5 of that book. So it's elementary. Okay. Any questions before I change subject? Yes.
Can you just repeat what k plus and k minus are?
Oh, there are any two knots that differ in a single crossing. So the way I think of it, so for me, k plus is, I have a crossing. This is a positive crossing, and this is a negative crossing by the usual knot theory conventions. Though which is k plus and which is k minus is not important because I haven't said how the gradings change. But going from plus to minus preserves grading, and going minus to plus drops it by 1, I think, or the other way around. So it's a definite amount. Any other questions?
Is your homology filtered somehow?
Okay, so I defined the associated graded object when I said you don't cross x's. There's a better theory where you're allowed to cross x's, and that theory is now a filtered chain complex. The full complex, the homology of the total complex is just a polynomial algebra in U. It's not interesting, but the filtration is interesting. And this is the associated graded object. And of course, if you had knots in an arbitrary three-manifold, then that would, the statement, the more general statement is that if you have a knot in a given three-manifold, then that knot gives a filtration on the Floer complex of the three-manifold. So this is a special case of that. Any other questions? That's chapter 13. Okay, all right, so now, having spoken for 15 minutes, I will now, in my remaining 45 minutes, give the second object. Okay, so this is all a combinatorial formulation of an invariant for three manifolds, which, if I had more time, I would give background on gauge theory and so on, but maybe I'll just skip straight to a definition. So the definition, and it's going to maybe look a little unmotivated, so you can feel free to ask questions. But what I'd like to do is I'd like to associate to a three-manifold a graded, well, a vector space. And this is Heegaard Floer homology. So this was an invariant that was introduced by Unni and Zoltan around 2000. It's a venerable invariant, but I'm going to describe it. So how does a person give us a three-manifold? So what's the simplest three-manifold you can think of? Well, there's the three-ball. And you can add to it handles. That gives you a three-manifold with boundary, a surface of genus G if you add G handles. And there's a classical theorem in three-manifold topology which tells you that any compact, closed three-manifold, connected three-manifold, can be written as a union of two of these handle bodies. Or three-manifold can be written as a union of two handle bodies, glued along their boundaries. And if you like, this is a statement about Morse theory. You have a self-indexed Morse function on your three-manifold, single index 3, single index 0 critical point. Then you chop at level 3 halves. You have above level 3 halves has a single index 3 critical point, G index 2 critical points. Below I have single index 0 critical point, G index 1 critical points. This is U alpha. That's U. Okay, so if we chop along a Riemann surface along an orientable two-manifold, a three-manifold falls into two very simple-looking pieces. And those two pieces can be described combinatorially as follows. I'm going to just draw the belts of these handles that I attached. And that specifies the handle body that bounds the given surface. So that is to say, a closed-oriented three-manifold is specified by an oriented surface, G disjoint homologically linearly independent alpha circles, and G homologically linearly independent disjoint beta circles. Okay? When I say disjoint, the alphas and the betas can intersect each other plenty, but they have to individually only intersect. Beta circles are not allowed to intersect each other, and alpha circles are not allowed to intersect each other. So this is going to be a very concrete combinatorial way of describing a three-manifold. And the mathematical culture that we grew up in at the time told us that to a surface, we were supposed to associate a symplectic manifold, and to the alpha tori, we were supposed to, alpha circles, we're supposed to associate a Lagrangian in that symplectic, and to the beta circles, we're supposed to associate another Lagrangian. That was the kind of life that people lived back in those days. And what's the simplest symplectic manifold you can associate to a Riemann surface? Well, there's the point. That's really silly. There's also the Riemann surface itself, which is also silly. But there's a very natural manifold you can associate to a surface, which is called its symmetric product. We say n-fold symmetric product. So what's the n-fold symmetric product of a surface? It's just the space of n tuples of points on your surface, period. Except you're allowing, symmetric product means that you're allowing points to collide. Now, typically that's a fairly evil thing to do in a manifold because it stops being a manifold. But there's a wonderful miracle in dimension 2 that tells you that the n-fold symmetric product of the genus G surface is a manifold. And the key point is that the n-fold symmetric product of the complex line is a manifold. And what theorem is that? It's the fundamental theorem of algebra. Very good. A monic polynomial is determined by its unordered n roots or by its ordered n coefficients. Right? So this is a wonderful miracle of low-dimensional. So this is a complex manifold. Well, okay, if you think of sigma as a Riemann surface, then that gives this the structure of a complex manifold. And it's a complex manifold, and in our case, we're looking at the G-fold symmetric product. We're not looking at an arbitrary symmetric product. We're going to look at the G-fold symmetric product of sigma G. And it turns out that that has sitting in it, associated to my alpha circles, a very natural G-dimensional real submanifold, which is the product of the alpha circles. So I can look at. Is that you? No, it's me. You don't have to confess. I would have to confess. So we take the Cartesian product of the alphas, and that gives you a half-dimensional submanifold in this complex manifold. The Cartesian product of the betas gives you a different n-dimensional submanifold in this surface. Now, what I'd like to Heegaard Floer homology is the obstruction to pulling these two tori apart inside of this manifold. So the first obstruction that you can think of is the algebraic intersection number. That I call this T alpha, and I call this T beta. You can look at the algebraic intersection of this T alpha with T beta, right? So you can orient everything in sight, or if you orient the alpha circles and you order them, that gives you orientation on T alpha. You can orient T beta similarly, and this has an orientation because sigma is oriented, so it's got complex orientation. You can look at the oriented intersection of T alpha with T beta. It turns out that that is always equal to the number of elements of the first homology of the underlying. Or this is if the first steady number is 0. So the silliest obstruction to pulling them apart is not very informative. It has to do with the first homology. Okay, but we want an obstruction that uses more structure. So, and this is where Lagrangian Floer homology comes in. Floer introduced a chain complex. If you have a symplectic manifold and you have a pair of Lagrangian submanifolds, then Floer homology, there's something called a Lagrangian Floer homology, and you want topological hypotheses to be satisfied. Floer introduced a chain complex whose generators are the intersection points of these two Lagrangians, and whose differential counts pseudo-holomorphic disks. So I'm going to be very, very sloppy with all this. And part of, yeah, I'm just going to be sloppy with this, I'm sorry. But the idea is if you have a symplectic manifold, you can put onto an compatible, almost complex structure, and then that gives you a notion of what holomorphic means. And his differential counts. So those holomorphic disks play the role of gradient flow lines in finite dimensional Morse theory. So you look at you count holomorphic disks that connect x to y, divide out by a natural R action, and you let that be the coefficient of y. Okay. I said that kind of quickly. Let's come back to the case at hand. The case at hand Floer tells us that we should define a chain complex whose generators are the intersections of the T alpha with the T beta. And there should be a differential which is a sum over all Heegaard states. So what I want to look at, I'm gonna fatten up this construction just a little bit. So we've got T alpha and T beta.
So there's the implied statement that this is a symplectic structure, this symplectic power? Or?
Yes. So here's the thing. If you give me, if sigma is a Riemann surface, if you choose a Riemann surface, name of a Riemann surface structure, complex structure on this, think it's a holomorphic curve, then its G-fold symmetric product naturally becomes a complex manifold. And then we have no problem talking about holomorphic curves again. Okay? Of course, also, if sigma is if this is an algebraic variety, this is also an algebraic variety, and thus it gets a symplectic structure.
It comes from the Kähler form, the symplectic structure?
Yes. Kähler form on the, yes, that's right. So Kähler geometry gives you a symplectic form. Actually, we're talking about holomorphic curves, so we don't actually even care about the symplectic structure. We care about the complex structure. So okay. So all right. So now what we're going to say is, I wanted to split things apart. There are notions of Whitney disks. A Whitney disk is a disk in the G-fold symmetric product whose left arc lives in T alpha, right arc lives in T beta, and it connects to intersection points. So I'm going to count things in homotopy classes of Whitney disks. And I want to look at those for which a certain topological quantity called the Maslov index should be 1. That quantity is the expected dimension of the space of holomorphic representatives of D. So said nicely. Here's the complex disk. It's got I and minus I in it, and I've painted half of it red and half of it blue. And I'm looking at holomorphic maps from that disk into my G-fold symmetric product that satisfy these boundary conditions. And I want them to be holomorphic. This is a complex manifold, so it makes sense for when these curves are holomorphic. Now, this space, of course, is conformally equivalent to the strip. And the strip has a real automorphism group of translations. So I want to divide out by that real automorphism group of translations, and I want this to be multiplied by 1. And now another confession. To get an interesting theory, we have to also choose a base point on this surface. And then that gives you a codimension 1 subvariety, which is W times sigma G minus 1 of sigma. And now it makes sense to talk about the algebraic intersection number of that complex codimension 1 subvariety with your disk. So in order to get an actually interesting theory, we have to multiply U to the number of times U to that algebraic intersection number. If you don't do that, that's like setting U equals 1. Which is like a little bit like setting U equals 1 in our knot theory. It stops being interesting. But if you take care of this, you can either have this an invariant over f of U, or you could set U equal to 0. So we can ask only those disks that don't cross that subvariety. That also gives you an invariant.
Peter,
Yeah?
sorry. In a context, I know this is not going to be true for a Heegaard surface, but in a context in which a surface had boundary, could you do without W? Could you use the boundary as your?
Yeah, you can do that. That's right. I mean, yeah. Actually, we're going to talk more about things like that.
Good.
So, okay. So, all right, but. So there are two versions of this complex. One of them is when we have over U, and the other one is when we look at only those things where this algebraic intersection number is 0. That's like setting U equal to 0. Both of them give you 3 manifold invariants. So the theorem is that D squared equals 0 in this context. D squared equals 0 is a really an elaboration of it's an adaptation of what Floer knew in the symplectic geometry case. And the hard stuff is then to show that it's independent of all the choices that went into making this 3-manifold invariant. The 3-manifold invariant, dependent on a Heegaard diagram for the 3-manifold, you have to check that that the invariant is independent of what Heegaard diagram you chose. So it's a bit of a struggle. But I see that I'm now at 5 o'clock. So maybe for those of you who are going through all these talks, maybe I should give you all a chance to escape. Yes.
Here's a stupid question. Is this torus a Heegaard torus in S3?
Yes.
Okay.
That's not a stupid question. It's a Heegaard torus in S3. So there's some very natural sense in which you can put that in Heegaard torus in S3. And now we've got the x's are like these. The vertical arcs are.
That's why you have
Yeah.
All right.
Anything else?